And now William Spencer will talk to us about ViCAR, a visualization system for Cox.
Hi, so I'm William. I'll be talking about ViCAR, and this is joint work with Shah, Zielinski, Ben Caldwell, Adrian Lehmann, and Robert Brand. So ViCAR is a Coq library designed to ease some of the common difficulties working with instances of monoidal categories in Coq, as well as providing a visualization for terms of this form. So first of all, the Coq proof assistant is a proof assistant, been around for a number of years, gives us machine check proofs that have therefore a high level of confidence and good integration with things like software verification. But as a price to pay for this, we have to provide it a lot of detail. And the usual mode of proof is a tactic-based proof where you provide a series of commands that advance your proof, manipulate your hypotheses and your goal to prove what you want to prove, kind of analogous to a written proof, but with every detail included. And there's a lot of automation used to bridge the gap to make it a little bit nicer to work with without having to do every little detail. So ViCAR grew out of some work, sort of an attempt to generalize some work we did with a particular instance of the monoidal category, the ZX diagram. So let's look at that and some of the difficulties we faced there. So the project we were working on was ViCAR, which is a formalization of ZX diagrams, which are a particular monoidal category. They're a system of rewrite rules for ZX diagrams used to model quantum information and reason about that. And what we found in working with this is that we really wanted the nice visual nature of the ZX calculus. We have a good there's a lovely diagrammatic representation used, in papers and things like that. But in the proof assistant, you need to represent things directly structurally. And we found that, the terms that you see get very unwieldy. It's much harder. It's hard to see what's going on in a term like that. Oh, it gets worse. And so having a visualization that's sort of, a first approximation to a string diagram is nice because you can see the structure, you can see how the morphisms relate to each other. And it gets far worse. Knowing what that notation means doesn't make it easier to read, I promise. And this is also, not the easiest to read, but you can get a better sense of the structure, even when it is a little messy. But there's something also awkward in that we have a lot more visual noise here than in a string diagram. And that's because we're working in a proof assistant. We need to keep track of, in what order our morphisms tensor together, how, in what order are they composed even. None of these things are baked into the proof assistant, and all that detail needs to be encoded in these visualizations. So monoidal categories and proof assistants, we wanted to generalize to this domain. First of all, are there other uses of monoidal categories and proof assistants? Yes, lots of them. Classical examples like matrices and the simply typed lambda calculus, but also lots of novel, ongoing research. There's a group working with causal separation diagrams, their construction of causal separation diagrams, who reached out to talk about common work between that and the ViCAR project about monoidal categories. And then, as we've heard in this talk, there are lots of other interesting areas to explore, like algebraic reasoning. But there are these awkward things working with this in proof assistants that you need to keep around all this structural information that makes it really annoying to do the types of proofs you want to do on paper, and you don't have a nice string diagram representation. And it's not even obvious how you would interface with a proof assistant to do purely diagrammatic proof. So to address this, we created ViCAR. So I'm going to talk about, first of all, what is ViCAR, and then the visualization we get out of it, some of the automation to get a little bit closer to diagrammatic reasoning, and then the question of diagrammatic reasoning in proof assistants. So first of all, what is ViCAR? So it's, again, a common framework for reasoning about monoidal categories in the Coq proof assistant, and that takes the form of a collection of type classes where you can declare what categorical structure a particular type has. So you describe what are the morphisms, what is composition, all that. And for our purposes, we split the sort of data of categorical structures from the sort of coherence side. And that just means that it's quicker to get into visualization. If you just want to visualize and you don't need any of the automation, then you can just tell us what the data are. And if you want actual proofs about those things with our tooling, then you can give us the coherence. But that's just to explain. So Here, the notation here doesn't hugely matter, but I just wanted to show what we're doing. We have these notations in the Cox system. One thing to call out, we are using an explicit equivalence of morphisms, as is pretty standard, because strict equality is too strict for a lot of purposes in proof assistance. And then in our notation, we also use the diagrammatic compose because we're visualization focused. But this is basically just the standard definition of a category with morphisms, composition, subjectivity, and unitality of that composition. And this gives us a graphical language that, in string diagram form, the graphical language isn't particularly exciting. Some morphisms strung together on a wire. And similarly, in our visualization, we have a little bit more information that we want to keep around. For instance, we found it useful to label the objects. But we also have this box around the composition to indicate the associativity, and we'll see how that plays out. There's a little bit more. We have the same type of wire notation as string diagrams, and then for associativity, you can start seeing where sort of the structural issues come into play. In string diagrams, associativity is naturally encoded. That's the whole point. But because we are trying to help people prove things in the proof assistant, we need to show them the structure there. So that's sort of the difficulty that we run into there. And then, of course, we can define monoidal categories, more of the same. Again, sort of standard definition of monoidal categories and the necessary coherence. So we get another similar graphical language with similar types of extra detail that we add with the order of the boxes to indicate the order of tensoring, and also which of tensoring and composing is happening in which order, as you can see in the bottom example here. So once you declare the structure over whatever you're working in, matrices, ZX calculus, etc., you can then visualize a term in the monoidal category and get this sort of graphical representation of it, which is great. And you can do this for any term you want, but there is a lot of visual noise. There's a lot happening here in what ultimately isn't a very complicated morphism, especially at the sort of fundamental level if you can ignore the associators and uniters there. We want to be thinking about this as this string diagram. So to bridge that gap, we have some automation. So these are tactics that you call that are sort of mini programs that will do their best to try and apply some reasoning to help your proof along. So for first example, some things to help with associativity. RSOC, LSOC, right associate and left associate the goal. Very straightforward. Cancel isos, cancels isomorphisms with their inverses, and removes units. All very straightforward stuff, but nice to have around. A SOC rewrite is the one that's particularly interesting. It will try and rewrite using a lemma, but up to associativity. So let's look at what that means. So we're in this. I'm going to be sort of walking through this example proof. So here's what we're trying to prove. In this case, we're in a symmetric category and we have the braiding. And so we want to use the braiding naturality statement. So let's look at what that looks like. We have that if you have two morphisms that you stack on top of each other, composed with the braid, you can pull the braid through. Great. The problem is we don't actually have that structure in this statement. Even though F and G are next to the braiding, they're not associated with it. So if we just tried to directly replace that term, we can't do that. But a SOC rewrite allows us to do that rewriting, and it will reassociate. It doesn't look particularly impressive, but if you have to instead manually do all the reassociations, this proof is 5 lines, and it would otherwise be 30 probably, and that's a lot of mental effort to go through. And then similarly, cancel isos will cancel the inverse braiding with the braiding, remove the units. And now the only thing that differs, as we can see, is just tensor and composition are in opposite orders. And we can just finish that, and then the proof is done. So associativity sort of works primarily with categorical structure, but to extend to monoidal categorical structure, well, we start with foliation. This is a method where you take a diagram in a monoidal category, a string diagram is where it initially came from, and you sort of pull it apart a bit so that you only have one non-identity morphism at each sort of layer in the process. And so we implement that. We also add a weak foliation, which is sort of the same idea, but you don't require only one non-identity morphism. This is the point of this is basically that it can alleviate some of the difficulty of working with monoidal structures. For instance, the order of composition, tensoring get resolved, but it's a far cry from what we really want. You're still having to deal with structural isomorphisms, associators, uniters, et cetera. So what we really want is actual diagrammatic reasoning. But it's not exactly clear what that would mean and how to implement that. We want it to somehow automatically handle coherence, but also allow us to manipulate diagrams in some way. And it's fuzzy. So looking at a simpler example, categorical coherence. We're basically just looking at associativity and unitality of composition. So in a way, cancel isos and right association solves categorical diagrammatic reasoning. Any two diagrams that are equivalent purely at the categorical level without any semantics should be solved by these two tactics. Extending to monoidal categories, it's not super clear, but certainly we should have monoidal coherence, which gives us that any composition or tensoring of the structural isomorphisms, if two of those are parallel, then they're actually equal or equivalent in our case. And so we implement that for types with uniqueness of identity proofs. And this allows us to start actually building the mechanism for true diagrammatic reasoning. And what this looks like is an intermediate representation where we directly encode structurally in an inductive form the tensors and the compositions involved. And what that allows us to do is write functions that analyze that structure directly, and then we can just prove that those functions are correct. Rather than having to apply rules every time, we can write large-scale functions and prove that those functions have correctness properties. And this is a common sort of structure of machine check proof, and it's very powerful because it can also be very fast because now you just need to compute things. And this gives us the monoidal tactic, which basically says if two terms, when represented as string diagrams, would look the same, then this should prove it. So for instance, we have actually a term we saw before, which has a bunch of associators and uniters, but fundamentally is just this simple diagram. And the monoidal tactic effectively extracts that from that term, a sort of almost string diagram representation, a list of lists of morphisms. We have an F and an identity and then G, and it sees that everything else is effectively ignorable. And what we can prove is that given two morphisms, if these sort of list of lists representations are the same, then the morphisms are equal. And that is sort of the first step of actual diagrammatic reasoning of we can look at two morphisms just at the level of string diagrams and show that they're equivalent in proof existence and ignore the structure there. So there are a lot of, this horrible thing that we saw earlier is solved by the monoidal tactic. This is just, all of the manipulations here are purely structural. So there are a lot of places we want to go from here. Monoidal rewriting is the most obvious one. So similarly to associativity rewriting, we want to sort of search in a term in the monoidal category for a certain pattern and replace that with another pattern we know to be, another morphism we know to be equivalent. And that's a harder problem because you have sort of two dimensions to work with and the interfacing between the tensoring and the composition to work with. But this also would enable visualization that hides the structural isomorphisms and gives you actual string diagram representation. Because if you can, in your coding, ignore the structure by having this rewriting, then you can visualize in that way and have it be useful. Secondly, we want to have more levels of categories. Graded and symmetric categories have more complexity to automation around them. You need to think about interchanging things and the like, but we want to get there. And then also, in the physics project, for instance, and in other developments, there's sort of an alternative to talking about uniters and associators directly involving casts, and it would be good to have interoperability with that to make it easier to work with those systems. And then finally, with all this technology, it would be nice to make an actual interactive diagram editor connected to a proof assistant, so you can drag around a diagram and have that be formally checked proof. So yeah, so that's.
Thanks. Great. We have time for questions. I see one.
Sorry, just a question on that topic. So, in what you've done so far, did you find at all that you were ever hit by it? So suddenly something took a much longer time.
So performance is definitely one of the challenges, especially when you're working with tactics that need to search the whole term. This is a common issue with rewriting. We haven't tested our tactics on really big terms yet, but especially for the monoidal tactic, which is done effectively just through computation, we expect that should scale fairly well with the size of the structure, because it should basically be a matter of computing that representation.
I had a follow-up to that, to your answer. The list of list representation, where does that come from? The fact that you don't have a braid? Does that break when you have the braid?
Yes, so that's sort of, well, there are two ways to do that. First, one option, it's dealing in braided and spectral monoidal categories is a lot harder. One option would be have this representation be at the monoidal level and just have the braids be morphisms there. That's pretty weak. You know, you can do, at the point of symmetric monoidal categories, you have an actual graph representation, and it's possible that you could compute that graph representation instead, and then try to compute that the graphs are isomorphic in some way. That's also another sort of hard problem, graph isomorphism, but in the size of graphs that we'd be dealing with, probably computationally tractable. But a lot of proof involved. There's a lot of machinery involved in implementing the monoidal tactic. Proving monoidal coherence was actually very easy. There's a great paper that demonstrated how to do that in the ALF proof assistant in 1994 or something like that. So that's 1,000 lines, and then implementing the monoidal tactic, it's pretty quick. It's really not bad. You follow the recipe. The monoidal tactic is another 6,000 lines to build up all of the proof you need to do this.
Yeah, are the string diagrams isomorphic as graphs? Is the way we do it in MATLAB?
Yeah. Yeah, but then the proofs necessary to put that in, to get the proof assistant to allow that. We're working on that problem for the special case of physics now.
Oh, for that, yes.
Yeah, for the ZX diagrams, and so hopefully we can translate that as well.
It's just a very stupid question. Most of your answers make it more compact.
Yeah, there are a lot of visual modifications. Another thing we could have on here is customizability of the visualizer. I think part of the reason I personally haven't spent as much time on that is because I'm hoping we can get this monoidal rewriting working, and we can sort of leave behind some of the structural concerns and move to more of a string diagrammatic notation. But yeah, there are a lot of visual improvements that can be made.
That's very cool.
Graph layouts are towards
Yeah, thanks. Can you say a bit more about the applications you think? I wonder if the applications drive certain different kinds of proof strategy or tooling. You mentioned ZX, which is great.
Yeah. So the most sort of immediate application is just the ZX calculus. But I mean, we already have a project working on this, but we, with the increased generality of monoidal categories, we've managed to do things that we didn't do when thinking about it as as a specific instance. I think there are a lot of categorical structures. I don't know. Maybe we should talk after. I don't have a clear answer to mind.
But you said more about the ZX tool. So you have a ZX formula that you can run.
Yes.
And automatically writing with the ZX.
I'd have to defer to a more of an expert on the ZX formalization to talk about that, I'm afraid.
Why do you want to use the XP?
Well, there are a lot of reasons. Somebody could give a better answer, but for a basic reason, I understand that it can give a verified optimizing compiler for quantum programs. The verified being the cost part.
Question why it's called? Yeah.
If you're asking in more generality, that's a different topic. But
Given the answer is so that it will be formally verified.
yeah, it's all a bit circular. Yeah, yeah.
Here, any more questions?
So how hard would it be to push this to like higher dimensional things, so minority two categories? Is that like very, very hard, or is it something that's within reach?
We haven't tried it. I don't have an intuition. I found that I've looked a bit at Braden's metric. Those are very hard for their own reasons. You know, in theory, that should sort of be more of the same at a level higher, but I suspect there would be challenges in adding the other dimension. And also, I found it's particularly hard to do this sort of thing in arbitrary dimension because of the, just working the proof assistant. It's hard to do that step. So it would probably be manually at the 2 level, and if you wanted higher levels.
Yeah, that makes sense. The dependence on and.
Yeah, you get into a lot of awkward programming patterns. Yeah. Making work.
We'll have a few minutes. I think we're going to want to start the next talk on time at 12. Which gives us 5 minutes. Thanks, Les. Thank you, speaker.
Thank you.